Good morning, students. My name is Courtney Grimes. Once again, I'm from Denton Magnet School of Technology. I teach our Math 6 advanced course as well as our Algebra 1 for 8th graders. Last week, we didn't quite finish scatter plots, so we're going to quickly go over how to write a line of best fits equation and make predictions, and then we're going to ease our way right into our sequences. So let's begin where we left off last Friday. So we were creating a prediction equation from our line of best fit. Hopefully you remember that our line of best fit is just a model to represent the trend of a scatter plot. In this case, notice that we have all of this data and we need a line to represent the trend of this data. So number one, we wanted to create a line that will intersect at least 2 points, but also represent half of the data above the line of best fit as well as beneath the line of best fit. Once we're able to do those two items, we can then write the equation. The equation formula we're going to use today is the slope-intercept. And in order to write the slope-intercept form equation, we need a slope and we need a y-intercept. So as a quick review, here we're calculating the slope of the line. We found 2 points that are currently on the line. So in this case, we used the point 50, 90 and 35, 82. I'm just going to write those off to the side as a reminder of what 2 points we chose. We chose the x value 50. When x is 50, y is 90. We also chose the point 35, 82, where the x value is 35 and the y value is 82. The slope formula simply tells us to find the ratio of the distances between our y values to our x values. So we have y minus y divided by x minus x. And notice that's what we did in our formula. We have y minus y over x minus x. When we take the difference of our y's, we have 8. When we take the difference of our x values, we have 15. So the slope of this line is 8 over 15. You can simplify that and you'll get somewhere around 0.5 repeating or 0.5. That simply means in the context of our scatter plot that time spent studying to test score, if a student spends for every 1 minute of studying, a student can expect to receive a half a point on the test score. So that's our rate, that's our slope. Next, we need a y-intercept. Again, remember, we're using the formula slope-intercept form. And as a reminder, the slope-intercept form is y is equal to mx plus b. I'm going to write that off to the side. Y is equal to mx plus b, where x and y is a point from the line. Remember that we received 2 points from the line. If we're using the slope-intercept form, we only need 1 point from our line. So we have our xy, which is the point, and then the m is our slope. We know that the slope is 8/15. Notice that we already have the slope written in our formula here. Now, the 90 is the y value from one of the points. So 90 is my y value. And remember, we only need 1 point. So where did the 50 come from? Well, again, the 50 is from our point x value. So we plug in the values 50, 90 to represent the x and y, which is a point. And we also substituted in 8/15 for our slope, which is the letter m. Then we just simplify the expression. Take the product of 8/15 of 50 and you get 80 over 3. To isolate the y-intercept, because again, we're looking for the y-intercept in this case, to isolate the y-intercept, we have to do the inverse of having a positive 80 over 3 or adding 80 over 3. And the inverse is to subtract 80 over 3. And we're going to subtract that from 90. So 90 minus 80 over 3 is 190 over 3. That is where our graph is going to intersect the y-axis. Well, what does this mean? Now, 190 over 3, if I can remember, is around 63.3 repeating. That simply means in the context of time spent studying and test score, if a student does not spend any time studying outside of what they're doing in the classroom, they can expect to score around a 63%. But then our slope tells us for every minute the student spends studying, they can expect to earn half a point, okay? So our equation for our scatter plot is S is equal to 8/15 t plus 190 over 3, where S is our score and t represents our time studying. So we can now use this equation to predict other related values. We're going to start with extrapolation. If we go back to our graph and we look at the x-axis, which represents time spent studying, from the graph alone, we have a range of 30 minutes to 60 minutes. Let's take a look at the value that we've been given. It says if a student studies 15 minutes, what would the predicted score be? Do you see 15 minutes represented in our range on the graph? Like, do we visually see it? We do not visually see it. It's there, but again, our graph is representing 30 to 60 minutes. That simply means that that actual value is extrapolation because the time is outside of the range of the original times that are represented on our graph. However, the prediction equation will allow for us to take the time that was given, whether it's represented on the graph or not. We can substitute it into our equation for t because 15 minutes is time and t represents time, and simplify. So by doing that, I can replace x, which is also t, that's our domain, with 15. Simplify this expression. 8/15 times 15 is just 8. Then add 190 over 3, and you'll get about 71.3. That tells us that if a student studies for 15 minutes outside of class, they can expect to score around a 71 on the test. A next type of value is called interpolation. The interpolation simply means that the time is within the range. Remember that our range was 30 to 60 or 30 to 80? For this particular problem, it says if a person studies 42 minutes, if I go back to my graph, do we have 42 that's represented on the x-axis? If you answered yes, you are 100% correct. Since that value is represented in our range, that is considered to be interpolation. So now we can still take 42, plug it into our prediction equation. So here's our 42 to represent time. Whoops, take the product and simplify, and we'll get 85.7. So if a student takes 42 minutes of studying for the test, they can expect to score around an 86%. Okay, so let's consider this scatter plot and answer the following question. The equation for our line is y is equal to negative 1x plus 12. What would the prediction be if x is 14? Is this an interpolation or an extrapolation? We're looking for when x is 14. Here's my x-axis, the horizontal line. Do you see 14 within that range? We do not. So that will not be interpolation, so that gets rid of A. And C, it will be considered extrapolation because it is outside of the range. We can now use the prediction equation, substitute 14 for x to determine the y value. So I'm just going to do that off to the side. So that's negative 1 times 14 plus 12. Negative 1 times 14 is negative 14. We're going to add 12 to that. Can you tell me what the y value is? The y value is negative 2. So the correct answer would be D. So we've looked at scatter plots. we were able to determine whether or not a scatter plot is linear or nonlinear. If the scatter plot is linear, we were able to determine the association, also known as correlation, whether it was positive, negative, or no correlation. Then we were able to create a line of best fit, create an equation to represent the line of best fit, and then find values for a prediction using our equation. Okay, so now we're going to shift gears. We're going to look at sequences. Based on our standard, we can determine our goal. We're going to write arithmetic and geometric sequences, both recursively and explicit. And we're going to use these sequences to model situations and translate between two forms. So what are sequences? Looking for patterns in sets of numbers can be something you do for fun or something you do to find patterns in other contexts. Being able to recognize and describe patterns in sets of numbers is helpful in every area of thought imaginable. People in areas such as cryptology, solar energy, and poetry study these types of sets all the time. When a set has a specific pattern or order, it can be further described as a sequence. So when we're looking at a sequence, each entry in the sequence is called a term, and you're going to hear me refer to that a lot throughout this lesson. So for example, we have this sequence 1, 3, 5, and 7. So the term has a place, and we call that place a specific word. Then we use a specific notation to represent that place. So the number 1 here is our first term. The number 3 is the second term. The number 5 is the third term, and the number 7 is the fourth term, okay? We're going to continue to look at this to make sure we understand when we're talking about the actual value in the sequence and the place, known as the term in the sequence. So the ellipses, which is circled below, means that the sequence goes on forever. It continues. When a sequence goes on forever, it's called an infinite sequence. Now, if you have a sequence and those 3 little circles are not there, those ellipses are not there, that is a finite sequence. So our notation, as we study sequences, we need a way of naming the terms. So we have this little letter here with the number. We have a lowercase a, and then we have a small 1 underneath it. We read that as a sub 1. That's an indicator that that's the first term of the sequence. The next one, where it says a and that small 2 at the bottom, we read that as a sub 2. That's an indication of the second term in our sequence. And then finally, we have an a, lowercase a, with the little 3 at the bottom, that's a subscript. We read that as a sub 3. That is our third term in the sequence. And it goes on depending on how many terms are being represented. So for example, we have a sub 1, a sub 2, a sub 3, a sub 4. Remember that this is literally just telling us the place value of that number. So a sub 1 is telling me that the first term is 1. A sub 2 is telling me that the second term is 3. Then we have a sub 3, which tells me that my third term is 5. And then a sub 4 lets me know that the fourth term is 7. And the ellipses just means the pattern keeps going forever and ever. There are 3 ways to represent a sequence. We can represent a sequence as a list. We can represent a sequence as a function, as well as a table. And we're going to look at all 3 representations. So here's an example of a sequence. Consider the rule of perfect square numbers, given by a sub n is equal to n squared. That's our formula or the equation. Its sequence is 1, 4, 9, and 16. Now, some of you guys have probably already seen the pattern, and that's awesome. That means that we're able to identify the rule of our sequence. My first question states, what is the value of the 10th term? Okay, now remember, when we're referring to term, we use a lowercase letter with the subscript. In this case, we're looking for the 10th term. Well, we can use our formula, a sub n is equal to n squared, to find the 10th term. In this case, n is 10. So anywhere we see an n in our formula, we're going to substitute in the number 10. So a sub n is equal to 10 squared. Well, Ms. Grimes, where did you get that from? Where did the 10 squared come from? Well, go back to your formula. Do you remember that it says a sub n is equal to n squared? And we're looking for the 10th term, so I can rewrite that by substituting in the number 10 anywhere I see the letter n. So I wrote a sub 10 is equal to 10 squared. So now we just simplify. What is 10 squared? 100. So the 10th term in this sequence is 100. The next prompt asks us to evaluate a sub 20. Remember, the rule is a sub n is equal to n squared. In this case, n is 20. So everywhere I see an n, I'm going to substitute in a 20. So my a sub 20, or my 20th term, is going to be the value of 20 squared. 20 squared is 400. So the 20th term in this sequence is 400. Now part C is a little different. It tells us a sub n is equal to 256. Then to solve for n. Well, if I look at my equation, a sub n is equal to n squared. And remember, n squared is just n times n. I'm going to write that off to the side. N squared is n times n. They tell me, or my given is a sub n is equal to 256. If that's the case, n squared equals 256. And remember that n squared is n times n. So 256 is some number times itself. Do you know what number times itself gives us 256? If you said 16, you are correct. 16 times 16 is 256. So the value of n is 16. So we found our 16th term to be 256. Okay, so the definition of arithmetic sequence. An arithmetic sequence is a sequence of numbers with a common difference. That is so important. So we have a common difference that can be written in the form a sub 1, our first term, a sub 1 plus d, that's our second term, where d is our common difference, a sub 1 plus 2d, our third term, a sub 1 plus 3d, our fourth term, and so on and so forth, where a sub 1 is the first term of the sequence and d is the common difference. So let's just take a quick look at this. I have a sequence that states 5, 7, 9, and 11. What is the first term of this sequence? The first term, which we can also identify as a sub 1, is 5. Do you notice a pattern of difference between 5 to 7, 7 to 9, 9 to 11? That common difference is 2. So I have a first value with a common difference. This is an arithmetic sequence. Another example, we have 23, 17, and 11. can you identify the first term of our sequence? If you said 23, you're absolutely correct. Do you know how to notate that first term? Right, a sub 1. So a sub 1 is 23. We go in our sequence from 23 to 17, 17 to 11. Do you notice a pattern there? You should notice that from 23 to 17, there's a difference of -6. And then from 17 to 11, there's a difference of -6. So our common difference is -6. So our arithmetic sequence form, we have explicit forms. Our explicit form is a sub n is equal to that first term plus the term value minus 1 times the common difference, where n is the term number in the sequence and d is the common difference. So let's very quickly take a look at how we can write the first 5 terms of the sequence in the list. So my a sub 1, n is 1. So everywhere I see an n in my formula, I'll replace it with 1. So that'll be 6 plus 1 minus 1 times 3. Simplifying, that's 6 plus 0 times 3. Well, 0 times 3 is just 0. So my a sub 1 is 6. We're going to find the second term. Remember, second term is notated as a sub 2. Anywhere I see an n in my explicit formula, I'm going to replace it with 2. So that's 6 plus 2 minus 1 times 3. From here, we're just going to simplify. 6 plus 2 minus 1 is 1. Then we're going to multiply it times 3. 6 plus 1 times 3 is 3. 6 plus 3 is 9. So my second term is 9. And students, unfortunately, we're out of time, but hopefully you were able to get a good introduction of sequences, and you're able to locate patterns and create an equation for an arithmetic sequence. You guys have an amazing weekend. Congratulations, we've reached the end. Congratulations to our 2020 graduates, and you guys have a safe and wonderful summer. Bye.